So there's one additional elimination reaction that I want to talk about, which is based on one of my favorite new sayings that you've heard a lot. Alcohols are not good leaving groups. And because of the fact that alcohols are not good leaving groups, there is going to be an interesting way in which we can do an elimination from our structure that has an alcohol. And this is going to be what we call a dehydration. And a dehydration is going to be removing, that's what the D is going to stand for. And then hydration is going to be water. So we're going to be removing water or eliminating water from our reaction. So this is actually going to follow an E1 mechanism. So here I have this structure, and it's a benzene ring. There's a chlorine. There is then a alcohol that's going to be on a secondary position right off the benzene. Now, if we go and try to do an elimination reaction on this reaction, there's going to be a few problems. First, you'll see way at the bottom, I actually put a chlorine. Chlorine is actually a typical leaving group. If that chlorine is on your benzene ring, you're not going to actually make another double bond. Benzene's already pretty nicely saturated, and you're not going to be able to fit a triple bond, at least not in this case. We'll learn in Orgo 2 a few weird examples where we can do benzyne, YNE, a triple bond in a benzene ring, or stuff like that. But for our sake, no. For right now, we're not doing anything like that. So I can't do anything with that chlorine. That's not going to be a good leaving group. And if I look at my alcohol, my OH is also not a good leaving group. So if I look at the structure, I don't have any good leaving groups to actually be able to do chemistry. However, much like when we were talking about when we were thinking about our substitution, I can change alcohols into something else that make them able to leave. And we're going to use the exact same thing that we talked about last time, and that is using acid to generate a oxonium. And with that, we can then get an elimination reaction under our acidic conditions. So let's go ahead and actually kind of show that mechanism. So we have our base structure, and we have our alcohol. And that alcohol is going to have some lone pairs on it, and those lone pairs are going to have a good level of basicity. So you can react this with an acid, in this case sulfuric acid. I've shown one hydrogen explicitly with a bond because we can go and then we can remove that hydrogen and then generate our sulfate ion. So when I protonate that alcohol, that is going to turn into our oxonium, which is going to be that positive charged oxygen, and then we'll also get that HSO4 minus. Now, in this case, if we go and we add heat, water is going to be a good leaving group. So we can show that leaving, and we're going to show that by the electrons in this bond going to the oxygen to make the other lone pair. And sometimes you'll actually see in the reaction arrow, you'll have this kind of downward facing or upward facing, and we can say like minus H2O for water leaving. That could generate our structure, which is going to now be a carbocation on our key substrate. Normally, if we had a leaving group that was a good leaving group, like a bromine or a tosylate or a mesylate or an iodide, we would skip that entire first step and then you just show that leaving. Here, alcohol is not a good leaving group. So if we're going to do a dehydration, we're going to need to use an acid to turn that into our oxonium, and then that can leave as water. Now, once you have that, we can then go and do our second major component, which is doing the actual elimination reaction. So we have our carbocation. Now this carbocation is still susceptible to all kinds of rearrangements, similar to like what we talked about in our last chapter when we were talking about SN1. this can still undergo a hydride shift. This can still undergo some resonance rearrangement. So there's still some flexibility and things that you do need to kind of like keep an eye out for. Here, this is going to be on a benzylic position. It's going to be super stable. It's not going to do any weirdness. Exactly one carbon away, I have a hydrogen. And then you can use either your sulfate or water. In reality, water is going to be more common in your reaction, so that's going to be used. If you showed sulfate, I wouldn't mark it wrong. And that is then going to come and follow our E1. It is going to pull off our hydrogen and then push the 2 electrons that were on the bond between that carbon and hydrogen into the bond to fill that carbocation. That will then generate our product, which has a double bond, and it will also generate some more acid. And that acid is going to be, in this case, our H3O plus. You could also, if you did it with the other one, H2SO4, both of those are going to be acids. And here you can actually do this with just a catalytic, a small amount of acid, because you're going to be generating more acid that can continue to deprotonate and do this entire process. So long story short, alcohols are not good leaving groups. However, just like how we learned some strategies to still be able to do some nucleophilic substitution, there's also some strategies which we can do elimination. And eliminations are going to be dehydrations, and we're going to follow with that exact same process that we did in the last one. Add acid to make oxonium, water leaves, and then you do your normal chemistry. One of the big differences, because of the fact that you'll notice I am using acid, which is the same thing that you see in your substitution. If you see this heat here, that triangle, which corresponds to heat, that is going to be a key thing that makes us think that we're going to do eliminations. And we'll talk more about that in a future video.